First, I will explain Cauchy's integral theorem and the residue theorem. Let us begin with Cauchy's integral theorem. Consider a complex function, f of z. We evaluate its contour integral along a closed path, C. If the function is analytic on the path C and inside C, then the integral is always 0. What does analytic mean? Strictly speaking, a function is analytic if it is differentiable in the complex sense. But for now, you can think of it more simply. The function does not diverge. Examples. For example, f of z equals z squared is analytic everywhere. On the other hand, f of z equals 1 over z minus 1 becomes infinite at z equals 1. So this point is not analytic. This point is called a singularity. Real versus complex integrals. Now let us compare real and complex integrals. For real functions, integration is simple. There is only one path from a to b, so the integral is uniquely determined. But in the complex plane, the situation is different. We have a real axis and an imaginary axis. If we integrate from a to b, there are many possible paths. For example, a straight path, a curved path, or even a looping path. So even if the endpoints are the same, the value of the integral can be different. It depends on the path. Contour integral now. Let us define a contour integral. A contour integral is an integral where the starting point and the ending point are the same. The path forms a closed loop. We write a contour integral using a special symbol. We add a circle to the integral sign. This indicates a closed path. Cauchy result again. If the function is analytic inside the contour, then no matter what path we choose, the integral is always 0. Residue theorem. Next, let us move to the residue theorem. This theorem is similar to Cauchy's theorem. It also deals with contour integrals. Suppose f of z is analytic in a region D, and the contour C lies inside D. Now define g of z equals f of z divided by z minus a. Here, the point A is inside the contour. The numerator is analytic, but the denominator becomes 0 at z equals a. So, g of z has a singularity at z equals a. Now we evaluate the contour integral of g of z along C. The direction is counterclockwise. The result is 2 pi j times f of a. So we take f of z, substitute z equals a, and multiply by 2 pi j. This is the residue theorem. Let us look at an example. Consider z squared divided by z minus j. The singularity is at z equals j. Apply the formula. We substitute z equals j. This gives j squared, which is minus 1. Multiply by 2 pi j. So the result is minus 2 pi j. Finally, if the contour does not include the singularity, the integral is 0. And even if we change the shape of the contour, the result does not change. The value of the integral depends only on the singularities inside the contour.